Hi everybody. In the previous video, we introduced the ideas of Boltzmann factors and partition functions, and learned how to calculate the probability that a particle occupies one of a given set of energy levels. In this video, we'll see how the situation plays out when we have more than one particle, and by extension, in macroscopic systems. It turns out that things don't necessarily go as we would expect based on our everyday experience. I'd like to introduce this topic by starting with a question about probabilities in everyday life. If we flip two coins, what are the probabilities of each of the following? Both flips being heads, both flips being tails, and one flip being heads and the other tails. I'll give you a few seconds to think about that, and you can hit pause if you need to. These are the answers. There's a 1/4 probability of both flips coming up heads, and a 1/4 probability of both flips coming up tails. You can think of the two coin flips as being independent, so there's a 1/2 probability that the first one is heads, and a 1/2 probability that the second one is heads, and you can multiply them together 1/2 times 1/2 to see that there's a 1/4 probability of both being heads. Same goes for both tails. The reason why there's a greater probability of seeing one heads and one tails is that there are two ways to get there. If you think of the two coin flips as being flip number 1 and flip number 2, you can get either heads tails or tails heads and end up with one of each. In other words, the two coin flips are distinguishable from each other. We can label them coin flip 1 and coin flip 2, and as a result, you can have multiple ways of getting to certain outcomes. This seems kind of obvious, but we're about to see something that contradicts this when we think about small particles. Although events and objects are pretty much always distinguishable in our everyday experience, they can sometimes be indistinguishable when we think about very small particles. Particles are defined as distinguishable if they can somehow be labeled differently. This is the case with big things like coin flips, as we just said, and it's also the case with things like identical atoms in a crystal. In a crystal, atoms pretty much stay where they are, and we can label them atom 1, atom 2, atom 3, and not lose track of them. But some small particles are indistinguishable, which means they can't be individually labeled. Two examples of this that we're going to see often in this course are atoms in a gas, which move around so quickly that unless we're tracking an individual atom, we're not going to know which is which, and also electrons. The importance of this is that if particles are indistinguishable, it means that different permutations of them don't count as separate states. They are all the same state as each other. That should seem really weird. That's like if the two coin flips we were talking about were indistinguishable, and heads tails and tails heads counted as the same state, and having one heads and one tails was not any more likely than having two heads or two tails. Now we're ready to think about some math, and we'll start by looking at the partition function of distinguishable particles. In this example, we'll consider two identical atoms in a crystal, each of which has 4 energy levels, labeled epsilon 0, 1, 2, and 3. And those two atoms are independent of each other. Each one can be in any of the 4 energy levels. We already know how to find the partition function of one particle. So if we were only thinking about atom number 1, its partition function would look like this. We'll label it Q1, the partition function of atom 1, and it's the sum of 4 terms. The Boltzmann factors corresponding to each of the 4 energy levels, epsilon 0 through epsilon 3. And recall from the last video that beta is just shorthand for 1 over kBt. We're going to use this beta notation in this video because it's more compact. So this would be the partition function if we were only considering atom number 1. And because atom number 2 has the same set of 4 energy levels, the partition function for only atom number 2, which we'll call Q2, is the sum of the same 4 terms. But we want to think not just about one atom at a time, but the whole system of 2 atoms. For the system as a whole, there are 16 possible configurations of energy levels that these two particles can be in. Atom number 1 can be in any of the 4 energy levels, and independent of that, atom number 2 can be in any of the 4 energy levels. So there's 16 possibilities total that we can think of as 0, 0, 0, 1, 0, 2, etc. The energy of the entire system is going to be the sum of the energies of atom number 1 and atom number 2. When we write the partition function for the whole system, the energies within the Boltzmann factors are going to be sums of the individual energies. So it's going to look something like this. We're going to use capital Q to symbolize the partition function for multi-particle systems. That's something we'll see throughout the next few videos. And so this partition function, capital Q, for the whole 2-atom system, is going to be a sum of 16 terms that look like this. The first term, e to the minus beta times epsilon 0 plus epsilon 0, corresponds to the case where both atoms lie in the ground state. And so on. There's a term for each of the 16 possibilities. It turns out that you can take this sum of 16 terms and factor it out into the product of two sets of 4 terms. I highly suggest that you take some time to check my math on this rather than taking my word for it. And finally, I want you to notice that each of these sets of 4 terms is identical to the 1-particle partition functions above, Q1 and Q2. So we can rewrite this 2-particle partition function, capital Q, as the product of Q1 times Q2, the partition functions corresponding to each individual atom. To summarize, in this example where we had 2 distinguishable atoms in a crystal, there were 16 possibilities that all contribute to the partition function, and it came out that capital Q, the partition function for the whole system, was equal to the product of Q1 and Q2, the partition functions for the individual atoms. It turns out that this result is general for distinguishable particles. Capital Q, the multi-particle partition function, is equal to the product of all the lowercase q's for each individual particle. That means that for n distinguishable particles that are identical, meaning that each particle has the same set of energy levels, capital Q equals lowercase q raised to the n power. And if we're talking about a system that has on the order of moles of particles, n could be very large. Okay, now we're ready to think about indistinguishable particles, particles that can't be individually labeled. We'll start by defining the 2 classes of indistinguishable particles. The first are fermions. Our focus here isn't on particle physics, so we won't go into too much depth, but what you should know is that fermions have half-integer spin, and they can't occupy the same single particle energy state. Examples of fermions are protons, neutrons, and electrons. And you've probably already seen this property when it comes to electrons. You've probably seen the Pauli exclusion principle, which says that 2 electrons can't have the same set of quantum numbers, and that's a property of electrons being fermions. The other class of indistinguishable particles are bosons, and bosons can occupy the same single particle energy state. Examples of bosons are photons and deuterons, where deuterons are deuterium nuclei, or a proton and a neutron. So an even number of fermions can collectively be a boson. And these 2 types of indistinguishable particles behave differently when it comes to partition functions and occupation probabilities. Let's think about the partition function for a system of 2 indistinguishable fermions. Suppose 2 fermions each occupy one of these 4 energy levels, epsilon 0 through epsilon 3. The question I have for you is how many distinct energy states are there for this 2-particle system? Remember that the 2 fermions can't occupy the same state, and remember that because they're indistinguishable, switching the 2 fermions doesn't lead to a distinct state. I'll give you a few seconds to think about this. Hit pause if you need to. It turns out that if you put 2 fermions in this set of 4 energy levels, there are 6 distinct ways of doing it, shown here. 0, 1, 0, 2, 0, 3, 1, 2, 1, 3, and 2, 3. And remember, because the 2 particles are indistinguishable, if you switch the 2 particles, you don't get another state. Now I'll ask the same question for 2 bosons. If there are 2 bosons occupying this set of 4 energy levels, how many different energy states are possible for the 2-particle system? Remember, bosons can occupy the same energy state, but they're still indistinguishable, meaning that switching them doesn't lead to a new state. I'll give you a few seconds to think about this. In this case, there are 10 possible energy states for the two particles, the same 6 that we saw for two fermions, plus the 4 states that you get by putting both particles in each of the 4 energy levels, 0, 0, 1, 1, 2, 2, and 3, 3. To summarize where we are so far, we've enumerated all the different ways of putting two particles into a set of 4 energy levels. If the two particles are distinguishable, we said that there are 16 different ways of doing it. If the two particles are indistinguishable fermions, there are 6 ways, and if they're two bosons, there are 10 ways of arranging them. If we want to write out the partition functions for each of these 3 cases, they would just be sums of all of these terms, where each possible state gets a term. It's fairly straightforward to count out all the possible states when we just have 2 particles and 4 energies. But when the numbers of particles and possible energies get much bigger, it becomes tricky to count out the possibilities for indistinguishable particles, because you have to do a lot of counting of states that are multiply occupied, and that becomes unwieldy when there are lots and lots of empty states. Fortunately, it turns out that it's also not necessary for us to do all of this counting, because we can make a pretty good approximation of the partition function of indistinguishable particles, regardless of whether they're fermions or bosons. The idea is that for many of the systems that we look at, there are going to be a huge number of empty states. For example, if we're looking at the translational energies of gas atoms or molecules, there are many, many more possible energy states than there are atoms or molecules. So the possibilities in which multiple particles might occupy the same energy state are negligibly small. That means that the key difference between distinguishable particles and indistinguishable particles in terms of their partition functions is in the counting of permutations. If we have, for example, 3 indistinguishable particles in the 3 energy levels in this picture, this only counts as one state because they're indistinguishable and we can't label the particles differently. But if we have 3 distinguishable particles and have marked the distinguishable particles with different colors because we can label them, in those same 3 energy levels, there are 6 ways of arranging them, because there are 6 ways of ordering 3 particles. The way you can figure out that there are 6 ways of ordering 3 particles is that we have 3 choices for the first particle, times 2 remaining choices for the second particle, times 1 remaining choice for the third particle. So that means there are 3 factorial permutations of 3 particles. That leads us to a nice approximation that we can make for the partition function of indistinguishable particles, regardless of whether they're fermions or bosons. As we saw earlier in the video, if we have n distinguishable particles, the partition function for the whole system capital Q is equal to the partition function for an individual particle lowercase q raised to the power n. We now know that we can take this partition function for distinguishable particles and divide it by n factorial, the number of permutations of n particles, to get a reasonable approximation for the partition function of indistinguishable particles, regardless of whether they're fermions or bosons. So we can make the approximation for indistinguishable particles that the partition function for a multi-particle system, capital Q, is approximately equal to q to the n divided by n factorial. That approximation is the expression that we're going to use going forward, but before moving on, I just want to take a closer look at whether this approximation seems reasonable for the 2-particle 4-energy system that we've been looking at. When we put 2 particles in this set of 4 energy levels, we know how to write the exact partition functions for each case. If we have 2 fermions, the partition function is a sum of 6 terms, representing each of the 6 possible states. If we have 2 bosons, the partition function is a sum of the 10 possible states. And we now know that if we have 2 indistinguishable particles, regardless of whether they're fermions or bosons, we can make the approximation that the partition function is what the partition function would be for 2 distinguishable particles divided by n factorial, which in this case is 2, because there are 2 particles. We now have a fairly busy looking slide with 3 expressions, but notice that they're very similar to each other. All 3 of these expressions have the same first 6 terms. It's only in the last few terms that they differ. The exact expression for fermions doesn't have any contribution of states where both particles are in the same energy. For two bosons, there are those four terms representing the states in which the two particles have the same energy. And if we use our approximation, and I suggest that you work through this math yourself, it turns out that those terms are going to count half. So our approximation for two indistinguishable particles is going to slightly overestimate the partition function of two fermions, and slightly underestimate the partition function of two bosons. This is generally going to be true. And when our system only has two particles and four energies, the approximation isn't great. But for the real systems that we're going to look at that have huge numbers of empty states, the approximation gets better and better. You may be wondering why we've spent so much time talking about partition functions, given that when we introduced them in the previous video, we basically just said that they were normalization constants that you could use to calculate probabilities. It turns out that partition functions actually have a lot of meaning just by themselves, in that they're closely connected to macroscopic quantities that can be measured for systems. So I'd like to end this video by talking about a few ways that Q is connected to macroscopic quantities that we'll use as a jumping off point for the next few videos. As we've seen, the energy of an atom or molecule can be expressed in terms of its probability of being in a number of quantized energy states. When we actually measure the energy of a big macroscopic system consisting of multiple particles, what we're seeing is an average energy over many atoms or molecules. And that average energy can be expressed in terms of Q, the partition function. I'm not going to show the proof in this video, but if you're interested, you can look at it in the textbook. The expression for energy is here. Capital E inside angled brackets represents the observed macroscopic energy of a system, and it can be expressed as the negative partial derivative of the natural log of Q with respect to beta, where remember beta is 1 over kBt. Alternatively, if you'd like to work in terms of temperature instead of beta, you can say that the energy is kB times T squared times the partial derivative of ln Q with respect to temperature. We'll use this result in future videos, but for now just be aware that you can express the macroscopic energy of a system in terms of the partition function Q. There's also an expression for the macroscopic pressure of a system in terms of Q. This is also in the textbook if you'd like to see the proof. And it looks like this. The macroscopic pressure of a system equals kBt times the partial derivative of ln Q with respect to volume. Again, if you know the partition function and how it changes with respect to volume, you can find the pressure of a system. And the last quantity that I'll mention, since it's one that we'll be using a lot in the future, is the constant volume heat capacity, CV. This is basically the rate at which the energy of a system changes with changing temperature. Partial derivative of E with respect to T. So, given that we can find the energy E from the partition function, that means we can also find the heat capacity CV from the partition function. We'll be using all of these results a lot in the next few videos. That's all for now.